how to find the area between two curves. Now, previously we learned how to find area between one curve and the x-axis. Now, what we're saying is that there may be like two functions that are both above the x-axis, and we can find this particular area between these two curves. So that's what we're going to do. I'm not saying this is the exact curve that we're going to integrate, but we will be finding areas as such. So we want to know how to do this, how to find that area between two curves, and it has real life applications, so we're not just torturing ourselves. So the graph here is showing you y2 is that curve and y1 is the straight line. And if we first of all notice that no one's going to help us to calculate this, the limits may not be given to you straight away, so you have to find these points of intersection with just preliminary calculations with what you learned in chapter 2, 3, 4, where you solved simultaneous equation with substitution to find those limits yourself. Okay, in uh, in all cases, this is not the case that you will be given these limits. Finding these limits may be part of the problem itself. Okay, so that's not, you can find the points of intersection by substitution. So this is just use your knowledge from previous chapters to figure out how we figured out the points of intersection from chapter 5 and so on. Alright, so then we want to find this orange region. That orange region is initially part of this region where we subtract that purple region from it. So the methodology is to find the area under the upper curve and then subtract the area under the lower curve from it. Alright, so you need to know which one's above which line. You need to know which equations line above, which equations line below. Now, these two areas, once you subtracted them, will give you that orange region. Okay? Now, there is a methodology that will save you a little bit of time. In some cases, you can, what we're doing is you in performing this integration first, y1, and then subtracting the result of the integration y2. Now, it can be simplified by actually subtracting the functions from each other first and then performing only one integration, and that involves less work because your work will be much lighter, you'll have less limits to work with, you don't have to do this 4 times, you can just do it 2 times once you subtract one function from the other. So let's see it in action because this will be somewhat simpler. Okay, so let's look at this example here. We've been told to find that orange region of the shaded area under the between those curves. It's not necessary under both curves. It's above the line y equals 2x and below x 4x minus x squared. So this, first of all, this notation tells you the roots of that negative quadratic there, so where the 0 and 4 come from, but we don't know this intersection point. So that's the first thing we need to figure out. We need to know where is that intersection point because that's the limit. This is like the upper limit of my integral. In any case, I need that. So let's do that first. So we set these two equations equal to each other and we try to solve this equation. So subtract x from both sides, we end up with this expression which we can factorize, and we end up with these two factors. One of them is 0 and the other one is 3. Therefore, this value where they intersect x equals to 3. Now we put that aside, and now that we know that's a 3, what did we say? To rather than performing two integrals and having these limits, you could have done like this. The long method is this minus x squared dx, and then subtracting 0, 3 and this. But we said that actually we can simplify this by just making one integral out of it. We can say, what's the multiplication of this? 4x minus x squared. Subtract x from it. Because this is the lower curve, you take the equation of a higher curve and you subtract the lower one from it. So what's 4x minus x is going to be 3x. We got that kind of equation anyway. So we can just integrate this function under those limits, and this will give us the area, the orange area, straight away. So what's that? 3x squared over 2 minus x cubed in front of it, evaluated as 0 and 3. So 3 square, 3, yeah, here's 3 square minus a third, 3 cubed, and substituting 0 there doesn't really change anything, because I see there is no constants. If there was a constant, it would matter. But here, 0 to the power of anything is still 0. Doesn't matter what, what the others are. So it will simply turn into 27 over 2 minus 27 over 3, which is 9 anyway. So I'm just going to write a 9 here. So what is 27 over 2 minus 9? It's it's 4.5. So the final area should be 4.5. Notice there's no need for a plus c or anything like that, because we have limits. This is a definite integral. Okay, so in some cases you can go along the long way and calculate the area of the triangle here. Sometimes with geometric shapes you may actually calculate this longer way. So I'm going to show you a longer way of calculating the same area. Should give you the same answer, 4.5. So method 1 is to calculate two areas. So this is the method I went through and I did this. No, I didn't. This is finding the entire area under the curve here, which is 9 square units, and finding the area of triangle half and subtracting the area of triangle 4.5 to get another answer, which is the same. All right. So this is the long method, and this is the shorter method that I chose to do for you by hand, and this is the answer you would have got. Okay, obviously this method I would prefer it to the other one. So in this next example, once again we are finding the area bounded by the x-axis and under the curve 2x and this area here. So what are we going to do now? The strategy, don't forget that if you find the area of the curve x squared minus 3x, you are going to, between 0 and 3, you're going to end up with a negative answer here, and you don't want that. You don't want to do that. I suggest, we already know that it has a root of 3. From its factorized form, we know that one of the root is 3, and it's indicated on the graph anyway. So what we can do is we can find the point of intersection. All right, this value, what is it? We don't know. We need to find that value for intersection. We can actually figure out, if I change my pen color there, we can find the purple area by integrating this function x squared minus 3x by using these two limits. Now, when you integrate that function, obviously the area under the curve is this purple region. And we can, once we know the area of purple area, we subtract that from area of this right angle triangle. We would have found the width of the triangle, and the height of the triangle is a simple piece of cake by finding the intersection point. Okay, so this point of intersection is key to our answer. So let's figure it out. All right, so we set these two curves equal to each other. If you should know that by now from chapter 2 and 3, where we solved simultaneous equations. Finding the intersection point, we end up with this expression, which can be factorized, and we give us x equals to 5. So the value of x there is not 0. Certainly 0 is the other point of intersection here, which we kind of could have guessed from the shape of the graph, and that's the origin. So 5, we're gonna put 5 there and wipe this off. Now, how do we know the y value of point C? We substituted in this expression here. 2 times 5 is 10. So that's where the y value comes from. Now we can already guess what the area of the triangle is. Okay, triangle area is going to be 5 times 10 divided by 2. Notice the graph is not drawn accurately, just to save you space, save us a space. The height is actually larger than the width, but we are in any case multiplying base by height and dividing it by 2, so we end up with 25 units square. So that's the area of the entire triangle. We're just going to calculate the area. The purple region, if you remember, is between 5 and 3. Okay, so once you evaluate the integral, we do this carefully with the calculator, and you end up with this expression, 26 over 3. So you need to say 25 minus this answer here. Okay, the area of the triangle was 25, and the purple region here had area of 26 over 3. Okay, so just some pointers for your examination. You do need to show you're working out. Yes, your calculators, if you have graphic calculators, you can even find the integral sign under the integral menu, and it can give you the answer. You can double check your answer if you get some time in the exam, which is rare. So in any case, learn to show your calculations here and write your what values you substituting, because these lines here will get you marks. They are worth marks in the test. So don't skip over them. They are important, right? So this should be everything for integration chapter. Now there are some questions you should be able to do. There is some extra that I had prepared for people who have knowing Riemann sum integration. This is not examinable, so you can skip over this section if you don't. In Riemann integrals are graduate degree level or university level mathematics. But if you were studying maths in the US, you may have to know it. So here I'm using this 4x plus 2 as my function as sum of integrals. So what it really means is, what we're going to do is, I'm going to show you the sum formula where you actually finding the height of each the function. We're going to use a limit as n. N here is just okay. So what I'm just going to